welcome to the lecture. The main agenda of this lecture will be to first recap some elements of Minkowski spacetime that we discussed in the last lecture, and then we will start discussing Lorentz Group. So let's start with the recap. So we know that Minkowski spacetime has an associated line element, which is defined by this expression. So here we are considering one time direction and three space direction, and the Minkowski spacetime with this number of dimension is denoted by this R3, 1. And the main difference between this line element from that of the corresponding Euclidean line element is that there is a minus sign in front of this time component, and hence it captures the notion of causality between two states. And then we discussed three cases that emerges from this. First one is the time-like separated distance, where ds square is less than 0. Now for this case, you can always go to a reference frame where you set dx, the spatial part, to be 0. And then if you define the time measured in that particular frame by tau, we will have d tau is equal to dt by gamma. Gamma, remember, is 1 over square root of 1 minus v square by c square. This is the Lorentz factor that we defined in the previous lecture. Now, this tau is known as the proper time, which is the time measured in the rest frame of the system. So the example of time-like separated distance is that you take any 2 points on a trajectory of a point mass A moving with certain velocity v, and the distance between any 2 points on this trajectory will be time-like separated. And then we'll have a space-like separated where ds square is greater than 0. And here you can always go to a particular inertial reference frame such that you can say dt equal to 0, that is the events happening simultaneously, but dx remain non-vanishing. And if you measure the length of the object in that particular reference frame, it is known as the proper length. So for time-like case, this relation gives us the time dilation, and for space-like case, this gives the length contraction. And then we'll have a null or night-like separated distance, which is ds square equal to 0. And you can show that there exists no rest frame for this case, because if you try to go to a frame where dx is equal to 0, then this will imply that dt has to be 0, so things will become trivial. And this is consistent with the fact that you cannot define a rest frame of light or photon. And then we have drawn the locus of points, equidistance from a point, say, let's say the origin, which are time-like, space-like, and light-like separated. And we have drawn it here again. So these blue lines, these which is at angle 45 degree, give the double light cone structure. The red lines are the locus of the time-like separated points with respect to this origin O, and then this green one are the space-like separated. So remember that space is homogeneous as well as time is homogeneous. So it doesn't matter which point in the space-time you fix as a origin. You can choose any point, and in all of them will have its own light cone. So whatever point that lies inside the light cone of a given point will be causally related to that point. Okay, and this gives us the following important fact that for time-like and light-like separated event, we'll have a Lorentz invariant notion of time order. If you start with two events which you can dub as cause and effect of each other, then this time ordering will remain same for time-like and light-like separated event. But for space-like separated event, you can always go to a reference frame where you can reverse this time ordering. So there is no notion of cause and effect for space-like separated. Okay. Now we will try to discuss essential points about Lorentz group. Let's start with that. before that, let's rewrite this Minkowski line element in terms of matrix multiplication. So, dA square, you can write in the following way. Remember that we can write this coordinate differential in terms of a column vector, okay, which takes 4 entries. First one is dx0, and then these three are the spatial, corresponds to the spatial direction. And then because this is a scalar, just a number or a function, so you can rewrite this in the following way, that you have this dx0, dx1, dx2, dx3 dot, and then there is a row vector dx0, dx1, dx2, and dx3 multiply 4 cross 4 matrix, take this diagonal form. So you can multiply this, and we will say this is equivalent to dx0, dx1 square, dx2 whole square plus dx3 whole square. And this metric is known as the Minkowski metric, which will denoted by the symbol eta. 1, 1, 1. These are diagonal component, and it is evident that Minkowski metric is symmetric. Eta is equal to eta transpose, and also it is self-inverse, which means that eta square equal to 1. Minkowski. Okay, and then we know that under Lorentz transformation, how this coordinate changes. So let's try to write it down. So we write the ds square again in terms of the matrix. So this is dxt transpose, means it's a row. Then you have this eta, and then so you have to think that this is like a matrix. The row, this is a for metric, and this is a column. Now we know that this coordinate transforms as x and x plus a. So this is the Lorentz transformation, and this is a translation. So it's a constant shift, and as we will consider in differential, it essentially doesn't matter. So this gives the following: x prime times dx. So remember that these Lorentz transformations do not contain x, the coordinates. So it's just a function of the uniform velocity parameter, or we'll say it can be rotation matrix also. Essential point is that when you take differential, you have this. So now we know that ds square remains invariant. That means dx transpose eta dx, and then replace this by the following: lambda times dx prime eta times lambda times dx. They should be equal to each other. This line is nothing but the prime line because this is ts prime, right? Which is tx prime times here. So now if you compare these two, the metric is invariant. So before that, first let's rearrange this line. So this line rearrange will be tx transpose the transpose theta lambda and dx. Now if you compare this with this, we will get the following: lambda transpose theta is equal to eta. Okay. And this is the definition of Lorentz transformation. That means Lorentz transformations are those transformations which preserves this metric eta, which is the Minkowski metric. Of Lorentz transform. Okay. So if you look at it closely, then if eta has all entries plus 1, then it would have been just the identity matrix. Then lambda would have been just a orthogonal matrix. But remember, the first entries of eta is -1. So remember that eta is -1, 1, 1. So this first entry we denote by eta 0, 0. And these three entries will denote by eta I, where I runs from 1, 2, 3, and of course the off diagonal elements are 0, which means eta I 0, which eta 0 I is 0. So because of this minus sign, it spoils the orthogonality. Rather, we call these matrices which satisfy this relation, that is the Lorentz transformation matrices, are pseudo orthogonal matrices. Lambdas are pseudo orthogonal matrix. Now, we will show that if you considering all possible Lorentz transformation defined by this relation, they satisfy the properties of a group, and we call that as a Lorentz group. So let's try to show that explicitly. So to show the that they satisfy the properties of group, first we will check the closure property under multiplication, which is to say that let's take two Lorentz transformation, lambda 1 and lambda 2. Then if we multiply them, we get some lambda, and lambda is again a Lorentz transformation. That means we have to show that this lambda also satisfy this relation, given the fact that each of these lambda 1, lambda 2 satisfy this equation. Okay, let's try to show that. So what we have to do is that let's start from this transpose times lambda, which is lambda 1, lambda 2. And we use the fact that transpose of a product of two matrices is equal to the transpose of the individual matrix, but in the reverse order, which means that this gives lambda 2 transpose and 1 transpose lambda 2. But now if lambda 1 itself a Lorentz transformation, then this will be eta. So we have lambda 2 eta times lambda 2. Again, lambda 2 also a Lorentz transformation. So it will satisfy eta. And hence we have our relation. So product of any two Lorentz transformation are also a Lorentz transformation. So it satisfies the closure property of. Now next is the associativity under multiplication. So now this should be obvious because all these matrices denoting the Lorentz transformations we have written down explicitly, and we know that matrix multiplication is associative. So it's obvious that lambda to satisfy these. Because of the fact that matrix multiplication are associated. Okay. Next, we have to show that inverse exists, and that inverse element is also a Lorentz transformation, that it belongs to the group. So let's denote the inverse by lambda inverse, and we have to show that it satisfies the defining relation of the Lorentz transformation. The inverse transformation. Now remember that again we start from this and we multiply this equation lambda theta lambda. So multiplied by this side the lambda inverse, and then this side by lambda t inverse. So it will have that inverse theta lambda inverse is equal to inverse, which is to say lambda inverse hence you can see that lambda inverse itself a Lorentz transformation and belongs to the group. Inverse exists. And the last one, we check that identity exists. So identity under multiplication, that means lambda times this identity matrix, which we denoted by this Li, this, and we have to show that I also a Lorentz transformation, and that is trivial because I transpose eta, I is eta. So also Lorentz transformation. So we have now proved that all possible Lorentz transformation forms a group, and we call the group as Lorentz group, which we denoted by O3,1 symbol, the Lorentz group. Now, what this 3 and 1 means, 3, 1 and 1 is referring to the signature of the underlying spacetime. That is, it is counting how many number of positive and negative eigenvalues the Minkowski spacetime has, and we know that it has 3 positive eigenvalue and 1 negative eigenvalue, and hence we are saying that the Lorentz group is denoted by O3,1. Remember that makes it different from the corresponding orthogonal group, which gives the corresponding Euclidean matrix without the minus sign. So it's a group of all pseudo orthogonal matrices. Pseudo and remember we are working in 3+1 dimension. Now let us make one comment that you can think these Lorentz transformations are a special case of something called a metric preserving transformation, and Lorentz group is a special case of metric preserving group. So let's briefly discuss that. Metric preserving group. So given a metric G, at this point G is not the Minkowski metric, and if we have a set of general invertible linear transformation which is been given in the form of a matrix, so the definition of these metric preserving groups are that capital G T G okay. These are the set of linear invertible transformation which keep this matrix small g invariant matrix. Transformation or matrices. So let's take a few examples. So if when G is identity matrix, that is this, we know that capital G identity, which is nothing but the orthogonal matrix. So when G is of this form, minus I Q times Q so it basically it's a diagonal matrix with the Q number of -1 and P number of +1 is the generalization of the Minkowski metric. So we can see that G's are in this case is P plus Q cross P plus Q pseudo orthogonal matrix. So when Q is equal to 1 and P equal to 3, this gives us to the Minkowski matrix, and we have the group called Lorentz group, which is O3, 1. In general, this group is denoted by O, P, Q. So when P equal to 3, 1, this gives O, P, and another example is when G takes this following one 0 n cross n identity matrix. So remember, now the diagonal elements are 0. You have off diagonal elements. So here there is a identity block which n cross n dimension, and there is the minus of identity of which n cross n. Remember, these are itself a n cross n matrix, right? So the dimension of G is actually 2n cross 2n. So in this case, the set of all possible transformation which gives this particular matrix invariant is called as symplectic matrices, and they form a symplectic group. So they form something called a symplectic group N. This is a 2n matrices. Okay. And if you remember your Poisson bracket from classical mechanics, symplectic transformations are those set of transformations which gives the Poisson bracket structure invariant. Basically, they correspond to the canonical transformation that you are familiar from your classical mechanics. Okay. So now, given this, let's write down again the defining relation or the Lorentz group given here. So from now on, we will actually keep on using this particular definition to do many computation. So now, if you take the determinant from both sides, and using the fact that determinant of a transpose of a metric is equal to the determinant of the metric, and determinant of you will have both sides the determinant of eta that will cancel out. So determinant square is equal to identity, and this implies that determinant will be either +1 or -1. And based on this criteria, we can actually classify the all possible Lorentz transformation into two set. One will have determinant the one which we call proper Lorentz transformation, another set -1 called improper Lorentz transform. In fact, in the next lecture, we will take example of this two set of Lorentz transformation. We will also discuss another way of classifying this set of Lorentz transformation. Then we will combine all of them. So we'll end here, and thank you for listening.